Hi. So thanks for everyone for joining so early. My name is Pavel Levin. Like I've said, I work for Booking.com, and this talk is about using sequence learning to predict trips, destinations within a trip. So I'm a data scientist at Booking.com. Booking went a long way from being a small Amsterdam startup, and currently we're one of the largest travel e-commerce companies in the world. And recently we opened a new development center here, well, not here, but in Tel Aviv. And we're hiring. And this work that I'm going to talk about now is an example of something we worked on actually in Israel office. So the most important facts here are that we're handling a lot of reservations per day in a lot of different destinations. So the problem of recommending destinations is really one of the core problems for us to solve, and it features all throughout the customer journey on our website, the apps. So as soon as you land somewhere, we already have some context around what how to give you some kind of destination recommendation, and this context changes at different points. We know more or less about you. And we can use that to try to give you recommendations. And we do it on all platforms, on desktop, on mobile, in email marketing, etc. And this particular work is about recommended destination within the context of a trip. So you already made some bookings. We know you're going on a trip. What other destinations might be appropriate for that trip? So this is an example of one of the products that we have. Once you made certain bookings, we might assist you to help you where you can go next. So the plan for today is to quickly go over what's sequence learning in general, what's the multi-leg or multi-destination prediction problem, what are RNNs that we will use as the solution to the problem. We'll go over the implementation details, and then we'll discuss some of our actual commercial use cases and how we can generalize beyond the single-step predictions that we'll discuss. So what's a sequence model? A sequence model is a statistical model which gives you a probability distribution over sequences. So you have certain alphabet or a set of symbols that, in our case, they're destinations or cities, and we want to model how the sequences of these symbols behave. So we want some kind of meaningful meaning of the probability for each possible sequence. So the set of these sequences is usually infinite because they're sequences of unlimited length. A typical example to motivate is usually language model. So that's probably something many of you are already familiar with. Language model is, in this case, the sequence is a sequence of words or characters. So we can use it to unconditionally score sentences. For example, a sentence, she likes reading books, should be assigned a higher probability than she likes reading bookings, according to a good language model of English. There's also, we can also talk about conditional probability distribution. So machine translation would be one such example. Here we're conditioning the probability of a sequence on another sequence from another language. So this is actually an example of our in-house machine translation system for hotel descriptions. So given a Dutch sentence, how can we score different versions of translations so that the translation that is in fact the correct translation is assigned a higher probability? And we don't have to limit to working with the same modality. So, for example, image captioning, here we want to score a sequence conditional on some kind of representation of an image. So it turns out that trips are sequences too. And if you look at this example of very popular set of cities in Spain, it turns out there is a certain way to travel them that is much more likely than this other one that I made up. It's in fact several orders of magnitude more likely. So given this set of cities, you have a certain order that is much more likely than the other. there are many causal factors why that is true. For this particular example, it happens to be on the path of a common pilgrimage path. Also, the elevation profile makes it much more easier to traverse one way and the other. But whatever the reasons, there are certain orderings that are much more likely to occur than the others, and we can use that. We can benefit from it when we build in our recommendation systems. So similarly, if we already know the first 5 villages or cities where the customer goes, for this particular case, predicting that the next one is going to be Santiago de Compostela is much more likely than the next one being Barcelona, even though Barcelona might be unconditionally one of the most popular destinations, not just in Spain, but actually globally. So what's the multi-leg or multi-destination trip prediction problem? We have some kind of censored information about the trip. So we have a customer who booked a few few destinations in the trip, and we like to complete it by suggesting where else they can go to, which would make a good trip. And this particular work will focus on only forward prediction. So we already know where the customer will go, but now we want to extend where they will go after that. We don't care if they booked something, but they forgot to book something before. We're only doing the forward prediction. And I'll discuss a little bit the other problems at the end if I have time. So mathematically, the prediction problem is under our model parameterized by theta, we want to find the destination such that given a sequence of destinations, the probability of that destination is maximized. And the learning problem, conversely, is finding that model theta such that on average we predict correct next destination in the trip sequences. For the notation, the capital D will be the set of all of our destinations. The vector D is composed of individual destinations as our trip. Theta is our model. Probability of data given theta, we might abuse that notation as the likelihood of theta given D. And the next destination probability is written as dn given d1 to dn minus 1. So and the rest of this work will show you how we can use recurrent neural nets to solve this problem. So what are recurrent neural nets? Recurrent neural nets it's a generalization of a feed-forward neural network that allows you to model sequences, so events unfolding through time. They have 2 inputs. One of the inputs takes the current element of the sequence, and the other input takes the last representation that we learned at the previous step of the RNN unfolding. Each of these inputs is passed through a linear model in its most simplest form. We sum them, we activate them, and we get the current representation, what we've learned so far as the RNN cell. Optionally, we can have another linear model to the output, the projection layer, to predict the next destination or to tag current destination, whatever the need is. But that's actually optional. For destinations, for this particular problem, our destinations are actually symbols, they're discrete units. So in order to pass them meaningfully through a linear model, we need to convert them into something numeric, like a vector. So we have this additional layer of embedding, which takes a symbol or one hot encoded destination and turns it into a vector. And all of this is learned jointly. Yeah, if you're more mathematically, yes. So I'll cover it a little bit. If the question, if I used some kind of pre-trained embeddings from work to vec or whatever, no, I did not. So all the embeddings were trained jointly with the RNN in the context of this classification problem. And I'll show some pictures closer to the end why it actually gave pretty good results. So if you're more mathematically inclined, these are the formulas. We have 3 basic layers. We turn our destination into an embedding. We turn the embedding into the current representation, and we output the next destination. And yeah, the optimization problem is we want again to maximize this probability of the next leg under the RNN model being predicted correctly. So we use the log loss or cross entropy loss, which is equivalent to minimizing the model perplexity, which I think is a much more natural way to think of sequence problems. And let me try to motivate that. So let's say I'm going from Kyoto to Osaka, which is a very common segment in trips. And the question is, where am I going to go next after Osaka? So we have certain probabilities associated with this decision. We know that going to Tokyo is the most likely next case. We say is more than a quarter probability. And we go all the way down to Bat Yam with probability of 1/1,000,000. So what's the uncertainty associated with this decision of given Kyoto and Osaka moving to the next city? So we can use information theory to quantify it. In particular, if we use the Shannon information, we can have the amount of information attached to each of these outcomes. And if we average those, then we get the total average uncertainty or the entropy over this entire decision, or this random variable of going from Osaka to the next destination. So yeah, this is a kind of entropy, which if we exponentiate, we get how much uncertain. How should I put it? Basically, we're trying to see how much uncertainty there is in this decision. So this would be the equivalent of having an uncertainty of rolling a die with 38 sides. Does that sort of make sense? So we have a certain probability distribution with 50,000 possible outcomes, but we're saying that that certainty around this decision is equivalent to uncertainty of just rolling a 38 die coin. So we decrease the, so under this model, we're decreasing the effective number of next steps, likely next steps, to 38. And this is another way of looking at it. Yeah, so and the perplexity is this the average of that amount. So on average, how much uncertainty we have over the next decision. So what we want to find under this paradigm is the model that is the least perplexed by the data. So the model which has the lowest perplexity after the under the sequences that we observe in the wild. And it happens to be a very convenient thing because optimizing our cross entropy, we also happen to optimize the perplexity, which, as I hopefully convinced you, has a nice intuition behind it. So let's talk a bit about the implementation. So I used about 20 million sequences, 20 million trips from 2017 of our global bookers. I only looked at the top 50,000 destinations, and the reason for that is first it made it a lot more computationally tractable rather than using millions of potential locations, and it also covered everything pretty much very well. And I'll describe how we map to unknown destinations a bit later. So yeah, I also removed the consecutive stays. So in the same city. So if you book several hotels in the same city for whatever reason, you might want to split your stay, or you might want to explore different neighborhoods of the city, or you extend your business trip, whatever. I reduced that into a single stay, and that gave me a lot of sequences, which basically 90% of them were trips of less up to 5 different cities, which kind of makes sense. That's how people travel. They maybe 10% or so only travel on trips longer than 5 different cities. So next very important part is how we process the data so that it's friendly for our learning algorithm. So after I took all of these sequences, they're all trips of different length, right? So the easiest thing to do would be to just define some batch size and take those batches in the random order in which I output them. But there's a problem with that, because in order to feed this into this linear algebra machinery of our learning algorithm, I need to have a matrix to feed. So I would have to pad all of the elements of the batch that are not of the maximal length. And that would waste a lot of this learning energy to learn how to go from one pad to another. And that's quite significant and useless. So instead what I did, I sorted all of the sequences by length, and then I took the batches, which I would shuffle afterwards. So if we do that, then we only need to pad very few elements where you cross the boundary of the batch of the trip length from one to the next. Yes. Yeah, absolutely. So there's some kind of I mean, if you go to Tel Aviv and it's a part of two destination trip, it's one thing. But if it's a part of yeah. Uh, yeah. So if I understand the question correctly, are you asking if this sort of sorting by length would bias my training curriculum? Okay, so the short answer, it doesn't really, because of the amount of data that we have. So within each class of this trip length, we have millions of different examples. And maybe I didn't mention it, but after this sorting, we also shuffle the batches, which means that at this iteration of our stochastic gradient descent, you get sequences of length 2, at the next one left 20, and so on. So you still have this randomness without any systemic bias of how we're feeding the different probability trips. Does that make sense? Yeah, can talk later. Yeah, I put some sketch of how you might want to do it in in Python with PyTorch, the older version of PyTorch. I think the slides will be available, so you're free to play with it. Yeah, and when we actually get the trip from the batch, we want to split that into input and output. And input is the first n-1 elements of the sequence, and the output is the first to the end. So that we're always predicting the next element. So the model itself is so this is also kind of a sketch of quite straightforward RNN models that you can all try and play with. So we just have the embedding input pass through embeddings layer, going through dropout, going through RNN, and then another projection layer, a linear layer. For the next prediction, for the classification of the next category. And maybe the one noteworthy thing here is that I use this result from Soher, where you can tie the embedding matrix with the projection matrix to get it actually gets better result. So the intuition here is that the embedding matrix is of dimension, your hidden input times the number of destination, and so is the projection matrix. So, and they sort of trying to learn the same thing. That is, what does it mean for the two destinations to be close together in some vector space? So tying them together actually cuts down a lot of the model parameters, and it also helps with the training. And yeah, I tried without it, it didn't work as well. So training is a pretty standard stochastic gradient descent procedure where we shuffled our batches. We go through, as soon as we get fresh batch, we get our predictions, we calculate our loss, we backpropagate, and we update model parameters. And I have a demo actually. So for this demo, I took 1,000 trip examples from our data. only 1,000, not millions, and I'm running it on my laptop. And the goal is to show you how fast and how easy it is from just 1,000 examples without any fancy hardware to get a pretty decent recommender system. So let's load our libraries. Let's get our model. Let's load our data. Let's define the things. So what I'm going to do here is I'm going to run the model 10 epochs, so 10 passes through my 1,000 trips to learn from them. And after each epoch, I'll give a prediction on a very simple use case of a sequence of exactly one element, Porto in Portugal, and see what's the next, what are the next trip suggestions. Before I even start, I'll have the epoch 0 printed, so it's the prediction before the model trained at all, which should be some really, really random examples because the model hasn't even seen the data yet. So as you can see, you have some unknown place in Canada and so on. But already after the first pass, we've seen Lisbon as the top prediction. So after just a single pass with my laptop, we already get some decent predictions. And yeah, on epoch 5, everything is already in Portugal, which I think is quite amazing. Because people say, okay, for neural networks, you need all this fancy hardware and huge data. But here I'm giving you an example of 1,000 data points. Yes? I can show, actually. So this is what the data looks like, which are basically different sequences of different destination IDs. So, and yeah, maybe interesting to look at what the loss looked like throughout this training. So you can see that there's quite a bit of improvement initially, but by epoch 10, there's not that much more we can squeeze out of our 1,000 examples. So back to the presentation. Yeah. No. Yeah, good question. So these are the top predictions for the next element. So it's not a sequence. Yeah, good question. And yeah, if you want to play around with it without writing too much of your own PyTorch code, you can just look at the example from the PyTorch documentation of the word language model, which is a quite similar thing to what I did here, except how it does batching and a few other things. So this is what I was promising someone here around the embeddings. So the model, remember, it had this embedding layer, which gave you different vectors for different cities. And to me, it's quite amazing, actually, how without this specific objective of identifying countries or anything like that, it could learn pretty spot on how cities should be clustered. And again, without any direct supervision around the country boundaries, it clusters them quite well together. This is another example I really like because here you can see actually different Greek islands being separated by the model. And some of the confusion around, say, Macedonia versus Greek Macedonia is also quite understandable. Handle unknown inputs, also I had some question at some point. So, like I said, I limited my model to only top 50,000 examples. Which made things computationally much easier, and you don't have to deal with a lot of these long tail, low resource cities with not much data. So to deal, and but in production, people still book those things, so I need to be able to handle them. So the solution was basically to maintain a MySQL table that would map all of this unknown to my model destinations to the closest thing in terms of geography. And to do that efficiently, you can use KD tree. Probably many of you are familiar. It's a binary tree, which when you insert, your 50,000 destinations to this tree, it has this alternating dimension, latitude, longitude, so it will bucket them into it would put them into such data structure that that it will be very efficient to look up the nearest neighbor. And again, if you want to play with it, there's a very simple Python sketch of how you might want to do it using the SciPy package. The most important part, so I know I can do everything in my notebook, but eventually we'll have to put it in production somehow. So this is a very important part that a lot of data scientists, I think, underappreciate. So maybe it's good to describe a bit of our booking architecture in general in terms of putting machine learning model live. So we have a whole track that maintains the infrastructure for this. So we have all these workers that can handle, that basically designed to process machine learning inputs. And then we have our clients, which can be, something in the app or the backend of our website or email marketing or whatnot. And this client would send a single request or a batch request to get the prediction. So if you think of it, most examples on front end, for example, would be a single request because we see one customer at a time. But if it's something like again, email marketing campaign, then receiving a prediction for each of the million people that we need to send an email to would be a bit of a waste. So there we need to be able to handle batch requests. Each worker has access to some efficient model storage where we actually store the model, and everything that happens at booking is processed by our event stream, so everything has to be connected to it. To zoom in on the individual worker structure, it's a REST API. Which can be one of two different flavors. So I think most things that we do are the Java or Java native interface to some application like Pavel Levin or H2O or TensorFlow, or Java written, say, code to process linear models, which is quite popular, or k-nearest neighbors. But for this particular example, we used a different structure of the worker where we had the uWhiskey server with Python, where we would put our torch code inside of. And that way we still can benefit from all of our monitoring that comes with the worker, again, maintained by the machine learning track. And of course we get all the meaningful events that we can analyze later or do whatever with. For this and other machine learning problems, it's extremely important to have some efficiency. So if, like I said, Kyoto, Osaka is a super popular trip that's being called, many times per day, there is no point of calling the deep learning machinery every time it is called. So we cache the most common predictions. And again, there's infrastructure for that. And just to discuss some of the use cases, maybe if some of you ever booked something with Booking recently, you saw this type of bar that suggests you where you might want to go next. So that was one of the some of the use cases, right? Email marketing, again, definitely not all of the stuff you're receiving, but some of it in certain context is powered by the RNN, and there's some work in progress on introducing this into our mobile push framework. Like I said, the problem here was quite limited. We only looked at, given a sequence of destinations, how we can go to the next one. But in reality, people don't always book like that. So a lot of the time you will book something that in reality you will always book you will sometimes book something that is likely to sell out soon, which might be the end of your trip, or you're not sure where to go in the middle, but you know where you're gonna go in the beginning or the end because of the airport constraint. So sometimes there are lots of situations with the gaps, and there are different ways to handle those gaps that unfortunately I don't have time to go into now. But if you think of it, you can use the same model and just use the sequence scoring. So you can generate the top likely predictions for the forward prediction, and then connect it to the gap and score according to your sequence model, rank them in that order. You can also model it directly. Yes. I don't have anything to say about it, but it's a great question. Uh, yeah, sorry. So yeah, it's a good question. We do have access to a lot of feedback. For the work that I'm presenting here, the only feedback that we have is the actual bookings. So if we see that someone booked something, then we include it as the positive example, and that's it. But you're right, there are many ways to address the indirect feedback or the, say, closing irrelevant recommendation and so on, but this is not part of this work. So direct modeling is another way to handle the gaps. So you can actually have a model that has two inputs, what's before, what's after, and then you try to predict the gap. Additional user or trip or city level features. Just as an example, maybe the recent YouTube's recommendation system from Google is a good example of how you might use a sequence model with additional inputs. Another one that I really liked is use some kind of hierarchical encoding structure to model trips in the context of other trips. There's quite a bit of work right now on this hierarchical encoding of documents, where you have two levels of sequence model. One encodes a sentence, giving it a representation, and then the higher level will take each representation and encode it into a larger representation. That way you can actually output the representation of the next trip and decode it into the particular destinations. And I think that's all I have to say for today. We're hiring in Tel Aviv and in Amsterdam. And if you want to learn more about data science things that we do, please check out our blog. Thank you.